So we're going to move away from the lithosphere and look at the atmosphere. It's important to be able to describe and explain how air masses move on the Earth. So the main point to think about is that as sunlight strikes the surface of the Earth and heats the surface of the Earth, that air warms. And as it warms, it's got a lot of space between the molecules. So at the surface of the Earth, that air mass and those molecules get heated. And when I use the term air mass, think about it like a big block of air. That's what you want to visualize. So as the surface of the Earth is heated, that big block of air right over the surface of the Earth is heated. And when I heat up that air mass, that big box of air and those air molecules move further apart. They spread out and they become less dense. So there is a very small mass of air molecules in the same volume. And so as it rises into the atmosphere, and it rises because it's warm and less dense, and they're very far apart. As it rises into the atmosphere, it's going to begin to cool off. And so as that air cools off, those molecules start losing their kinetic energy. They move really close together and become a lot more dense. And as they become more dense, then they're going to fall or sink. Well, what do I create when I have an air mass that's warm, becomes less dense, rises, and then cools, becomes more dense, and sinks? You create a global wind pattern. You need to be able to just describe that process and not really look at all of the other factors, such as where exactly the trade winds and the westerlies are, but understand this idea of global wind patterns. So when we have these global wind patterns, they become big conveyor belts that transfer heat, but they also transfer moisture. So when you have temperature and precipitation, we looked at this last unit, you have a climate pattern, and climate patterns determine patterns of biome distribution. So in the big scheme of things, if we're connecting these two units together, you can describe and explain the processes so that you can relate global conveyor belts of temperature and precipitation and the broader environmental issue of what biomes are created in the different areas that they are found in. The way to think about it is that when you have this low density warm air mass, there's all kinds of space between those air molecules, and that allows for a lot of space for little water molecules to slip in. And it doesn't work quite that way with a cold air mass where the molecules are really close together and very dense. There's just not room for those little water vapor molecules to slip in there. As we have these global weather patterns in areas that we have cooler air, it's also going to be rather dry relative to the warm air masses. So when we start talking about these, we are also relating it to the water cycle or the hydrologic cycle. As those warm air masses that can hold all kinds of water rise and cool, it can't hold as much, so we get condensation and then precipitation. So if you look at the diagram, there's a direct relationship between temperature and the moisture holding capacity. The warmer the air masses are, the more moisture they can hold. And at the surface, they can hold more, but as they rise up into the atmosphere, they can't hold as much water molecules, and we have falling precipitation. Okay, so let's step back for a minute and go back to how the Earth's surface got heated to begin with, and why aren't every place on the Earth the same all the time? If we always have these areas of the earth that are heating, and it's heating an air mass, and the air mass is rising and letting go of moisture, and we create these patterns. Why don't we just have the same pattern or band all over the planet? And that's where we need to bring to view this concept of solar insolation. Solar insolation is the same thing as incoming solar radiation. Um, and so when you look at this diagram, it's if you think about our Earth as a cube, if it were flat and we talked about solar insolation, then we would have the sun always striking the Earth at the same angle, whether it was the North Pole, the equator, or the South Pole. But our Earth is this beautiful sphere. So as you curve up towards the North Pole, you're going to get curvature to the North Pole, and the sunlight coming in from solar radiation, it's not striking straight on at the equator. Well, and 0 degrees latitude is the equator. So at 90 degrees north or south, you get a curvature of the Earth. So the sunlight is striking at an oblique angle. So the same amount of solar energy at the equator is spread over a pretty concentrated small surface area. But because it's striking at a curvature and that sunlight has to come in and hit at an angle, the same amount of energy is spread over a much larger surface area as I move toward the pole. So we start to make a connection between where the biomes are located and the climate. So another thing that we would look at is how the Earth rotates on its axis. So you can watch the little video and it will really explain how, as the Earth rotates on its axis, it's going to affect the amount of solar radiation at different times of year, which is what we have referred to, since you were in kindergarten, as the seasons. And then the last concept that we really need to touch on when we're talking about air masses right here is the rain shadow effect. So when we have an ocean or a large body of water, wind is going to come from that onto the landmass, and as it rises in altitude, because it's an air mass, we know that as it rises in altitude, it's going to start cooling and condensing. And so it gets to a certain point where it can't hold that water vapor anymore. So it's going to cool and condense before it ever gets to the other side of the mountain. So on the side of a mountain that has a body of water next to it, we will have a lot of rain and precipitation. And as that air eventually moves across to the other side of the mountain, it's lost all of its water vapor because it cooled up to a point where the water molecules were close together and all of the air molecules are close together, and the water vapor has already condensed and fallen out as precipitation, as either rain or snow. Then when you get to the other side of the mountain, we have a very dry air. So when we have large mountains on the other side of the mountains, you're going to usually have deserts or something. So here we have a picture, in addition to the little cartoon, we have a picture of the state of Washington, and you can envision that as warm, moist air comes off of the Pacific, it's going to hit that mountain range right there in the middle. It's right here. This is called the Cascades. It's going to hit the Cascades, and before it gets to the Cascades, it's going to continue rising up. So on the Pacific side of the Cascades, they're going to have a lot of rain or snowfall. And by the time that it gets to the other side of the Cascades, we have a really dry landscape. So that can really affect the ecosystems in an area also. And at the same latitude, we can have a very dry ecosystem at the same latitude as a much more moist ecosystem because of the rain shadow effect, where a mountain essentially blocks the rain from getting to the other side of the mountain.